Okay guys, let's take a look at today's lesson. We're going to be looking at functions of two or more variables. This lesson is a lesson that will help us as we prepare for multivariable calculus. You know, typically the students that are in multivariable calculus are tag students. The vast majority are tag students because they're more quickly advanced, right? They're ahead. So what we're doing is we're looking at more than one variable. So functions of two variables, we would have like this. The perimeter equals twice the length plus twice the width. I have two variables right here. We're not accustomed to graphing two variables, right? We don't do that. So that's multivariable calculus. It has more than one variable, right? It's got a couple of variables, 2 or 3 variables. So if we were to graph this, we would need to actually physically graph it in a three-dimensional plane. You know, here in this three-dimensional plane, this would be a graph of the perimeter. So notice how I have width on one axis, I have length on the other axis, and I have the perimeter on the z-axis, and it makes a plane. That's how I would graph something with two variables in it. Now, we typically don't graph things with two variables like that because we really, it's kind of easier to see on a two-dimensional surface, but to make a three-dimensional surface on a two-dimensional surface, we have some, choices of what we could do. So I have a couple of different choices. If we're going to decide to graph the perimeter in a two-dimensional, coordinate plane instead of a three-dimensional coordinate plane, we have a couple of options. The first option would be to draw curves for various constant values of either width or length. So here is our rendition of that. The curves, this is called curves of constant width. So what I would do is I would hold the width as to a number like 1. Let's say the length of my object is 1. And then I would plot the length versus the perimeter. So if the width of my object is 1, what possible lengths would I have? And how would that affect the value of the perimeter? So this would be, this line right here would be a constant curve for the width of 1. And then I could do that same scenario with like a width of 2. Well, if the width was 2 and my length changed, let's say to 2, then what would my perimeter be, and so forth. So that's one way that we could depict a three-dimensional object in 2 dimensions. Another way would be to draw curves for which the actual perimeter is constant. And we would keep the, so that's this piece. We would keep the length and the width variable. We would allow them to change. And so if we allow them to change and we want our perimeter to be 4, then what options would we have for that? And we would draw the curve for a perimeter of 4 with variable lengths and widths. So that's a couple of different options, and we actually have a problem on the next page where we do things like that. So we're going to demonstrate how we would graph like that. This particular diagram right here, the pressure gradient force diagram, I'm kind of going over it. We will have some questions that have to do with it. I'm not saying that you have to memorize anything about a pressure map, the gradient force, but I want to talk about it so we at least familiar with looking at it. So these lines represent these lines represent our pressure, the pressure. So like 1012, that's the pressure along these lines, 1008 and so forth. The H is right here, represents the high pressure. So this location right here has high pressure, and as we move away from it, the pressure decreases. Think of it like the top of a hill or something, and as we move away from it, the pressure decreases. The L represents low pressure, and as we move away from it on all sides, the pressure increases in all directions. And you can notice by the numbers. See the numbers 1008, and then it goes to 1012. See how the numbers are getting larger? And here, this number is 1024, and then it goes to 1020. See how those numbers are getting smaller? So that's just an indication of what's happening here. These contour lines, these lines right here, are called isobars, and they're lines of constant eye pressure. of air pressure. So this line right here, all along this line, has air pressure of 1020. That's what those lines represent. They have that constant air pressure. The strength of the resultant wind is proportional to the isobar spacing. In other words, the less spacing, the closer the isobars are together, the stronger the pressure gradient and the stronger winds. So if you look right here, see how close those bars are together? So right in this area, the wind would be much stronger than in this area, right, where the bars are much farther apart. So the closer the bars just tells us, the less spacing is a stronger pressure gradient, stronger winds. That makes logical sense. If I'm going from 1024 to 1020, look how far of a space I have to spread that pressure out. Versus here, where I'm going to 1024 to 1020, that's a much smaller space in order to go from 1024 to 1020. So it's much faster, if that makes sense. So that is an example of a pressure gradient force on a weather map. Okay. So with that, let's go to our example on the next page. Just have one example. We're going to draw several different graphs. As far as this lesson, probably reading things off of the chart shouldn't be too bad. Graphing is a little bit more challenging, but not too bad. We're going to kind of work through it, and hopefully you'll be able to graph these in 2 dimensions as well. So the first one, we have the volume of a cylinder is given by this formula, which we all, of course, know. And they want us to sketch the graph of, we want our volume versus radius. Volume versus radius. So this is going to be volume, this is going to be radius. And we're going to hold the heights constant. Okay, so what I'm going to do is just go ahead and put the scale on here. So we need to go to 3 R's. And then our volume scale, we need to go up to 9 pi. So I'm going to go in the middle between pi and 9 pi and put 5 pi, and then go in the middle of each of those and put 3 pi and 7 pi. Okay, so that's the scale that we're going to use when we're going to graph our volume versus radius. Okay, so basically another way to write this is V of RH, because that is a function of not just R or H, but both. It's a function of both variables, R and H. Okay, so let's do that. Let's hold the height at 1. So I want the volume of R, and I'm going to replace H with the 1. So that's pi R squared, and H is 1. So that's what I'm going to be graphing, the pi R squared. So let's draw a table here. If R is 1, then my H, let's see what happens. So I put, where are we? So if R is 1, then my, and I don't need to draw the graph there, sorry. The first ones are much easier. We can just kind of visualize that without having to draw a graph. So here I am, my height is 1. So if my R is 1, then my volume is going to be pi, right? 1 times pi is pi. So my radius is 1, my volume is pi. Excuse me, yeah, my radius. If my radius is 2, so if my radius is 2, then 2 times 2 is 4 pi, so I have 4 pi. So 2 would take me to 4 pi. If my radius is 3, that would be 9, right? That would take my volume to 9 pi. And so this would be the curve. And it would continue going for an H of 1. Okay. So now let's look And let's make the h 2. So I'd have 2 pi r squared. And let's graph that. So when r is 1, 1 squared is 1, 1 times 2 pi is 2 pi. That would put my volume at 2 pi. When r is 2, 4 times 2 is 8, that would put me at 8 pi. And when r is 3, oh, that would put me at 9 times 2 or 18, that would put me way up here. So this would be our curve for h equals 2. Okay, are we okay so far? So now we took care of this one and this one. Now let's work on an h of 3. So we're going to hold the h at 3. Well, we're going to hold it constant. So that's going to be 3 pi r squared. Alright, so let's graph this one. So when r is 1, then we're at 3 pi for our volume. When r is 2, what is that? 2 times 2, 4, that's 12. Oh, we're already way up here. So this would be h equals 3. And that would be the graph that we would do for volume versus radius holding the heights constant. And of course there's an infinite number of heights that I could choose, right? You would either choose them or they would choose them for you. Are we okay with that? Alright, so the second graph, we're going to graph height versus radius, and we're going to hold the volume constant. So let's work on the volume being 36 pi. So if I replace volume with 36 pi equals pi r squared h, then if I solve for h, that's the easiest one to solve for, that's why I solve for h. If I solve for h and I divided both sides by pi r squared, then h is going to be 36 over r squared. Okay, that's what the formula I'm going to use to generate my numbers. Now this is where I need my little table, because this is going to require a little bit more calculation than the first one. Alright, so if my radius is 1, I put that in here and I get 36. Okay, that's really not going to fit on our grid very well. The grid over here I had r on the x-axis and h on the y-axis. And I went up to 9 here. And then over to 6. On the radius. So a scale of from 1 to 6 on the radius scale, and I went to 9 on the height scale. Alright, so 136, not going to be able to really graph that. So 2, what happens if my radius is 2? 36 divided by 2 squared would be 9. Okay, and what happens if the radius is 3? 36 divided by 3 squared, or 36 divided by 9 is 4. And then what happens when it's 4? I would have 36 divided by 16, which reduces to 9/4. Okay, so let's graph that. So at 2, I'm at 9. At 3, I'm at 4. And at 4, I'm at what, 2 1/4? So maybe here. So it looks like that, and that is v equals 36 pi. Okay, we okay with that? So let's do our other one. That's 72 pi. So when v is 72 pi, I would do my solution like that, and I would basically, height that's going to be 72 divided by r squared. So let's do our little chart. 1, 72, yeah, that's not going to fit. 72 divided by 2 squared, or 4, is 18. Still a little large. If I do my radius at 3, 72 divided by 9, that gives me 8. It's a little bit better. If my radius is 4, I have 72 divided by 16, which reduces to 9 halves. And then I just skip to 6 because that was a nice whole number. 72 divided by 36 is 2. So let's graph our second one, where our volume is held constant at 72 pi. So the 1 and 2 are a little bit large for me to graph. So let's go to 3. 3 is at 8. 4 is at 9 halves. And 6 is at 2. So it looks like this. And that would be V equals 72 pi. Okay, so that's an example of how you can take something in 2 variables and graph it in 2 dimensions. You would just have to, either choose or be told which of the 2 variables to hold constant. And actually, really, you have 3 variables. You have what it's equal to, and then you have the other 2 variables. So really, you have a total of 3 variables we're dealing with. This is called function in 2 variables, right? Because the function is in 2 variables. So on part C, it says if h is held constant, what happens to the volume when radius is doubled? So some of us could kind of logically think this out. I'm going to look at it with, we're going to work it out analytically. So if I took the radius and doubled it, that's what I'm looking at. I'm looking at the volume of the radius doubled. So let's plug that into our formula here. So I have pi, and my r I would replace with 2r h. So I basically get 4 pi r squared h. This pi r squared h is the volume formula, right? That is volume. This is volume. So basically what happens to the volume? It's quadrupled. Okay, the volume would be quadrupled. So when the radius is doubled, the volume is quadrupled. So volume is quadrupled. Okay, we okay with that? All right, let's go ahead and take a look at our daily work.